All right, so let us begin. Last time we talked about the relationship between limb soup and the epsilon definition of the limb soup, right? And I prove half of the results, right? So it's an if and only if part, and I prove one way. Now I am going to prove the other way around. Right, so let me prove this way. For every epsilon positive, right, there exists n belongs to natural number such that xn less than L plus epsilon for all n, and for all n bigger than n, and L minus epsilon is less than xn for infinitely many n. Okay, so we have this. Now we have to show that this implies limb sup of the sequence xn is equal to L. And so to prove this part, prove the converse part, let us assume that there is for every epsilon positive, there exists the natural number n such that for all n bigger than n, xn is less than L plus epsilon, and for infinitely many n, xn is bigger than L minus epsilon, right? So we will show the convergence. Right, so to do this, define the set as usual. AK be the set of all xn such that n bigger or equal to k. Okay, so that is the set xk. You remember this is the set we define when we talk about upper limit and lower limit, or limb sup and limbs in. When we talk about that, this is the set we define first, right? So it is given that, okay, so let's epsilon be positive also. So then there exists n belongs to natural number such that xn is less than L plus epsilon over 2 for all n bigger than n. Right, from this statement, right, so from this statement, we can see that there exists some n such that for all n bigger than n, xn is less than L plus epsilon over 2, right? So, and then we have another statement, right? There are this for infinitely many L, right? Right, so you have this. Right, because this statement is true according to our supposition, right? You know that supremum of an plus 1 is basically the set of all xn such that n bigger than capital N plus 1, right? So that is obviously all the elements are less than epsilon over 2, so the supremum will obviously be less or equal to L plus epsilon over 2. That this is based on the supremum properties we studied at the chapter 1. So that's obviously strictly less than L plus epsilon over 2. Right? right? So when we define upper limit and lower limit, we notice that supremum of these sets, A case, is basically a decreasing sequence, right? The sequence of supremums of the set AN is basically a decreasing sequence. So therefore, so when K gets bigger and bigger and bigger, the value gets smaller and smaller and smaller. So for all n bigger than n, right, all the supremums will be less than this. Right, so supremum of all a for all n bigger than n, supremum of an will be less than L plus epsilon, because supremum of an plus 1 is already less than L plus epsilon, and for any n bigger than that, the supremum getting smaller and smaller, so obviously strictly less than that. Now, right, so this is one statement you have. Now on the other side, you have another statement, right? So you have this kind of statement: L minus epsilon is less than xn for infinitely many this, right? Right, this statement, so you can say that xn is bigger than L minus epsilon over 2 for infinitely many m, right? Because epsilon is arbitrary for any epsilon. So for this epsilon also, you can say for epsilon over 2, there are infinitely many n such that this. But you all already know this is L minus epsilon, so that's not a big surprise, right? So right, so because this statement is true for infinitely many n, right? So that those n can be any numbers, right? So there are many infinitely many natural numbers. So among those natural numbers, you can find the smallest one, right? Least natural number among them, right? So those n can be 2, 5, 10, 25, 125, blah, 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 like that. It goes up to infinity, right? So among that, you pick the smallest number. That is not a big thing, because you all know the set of natural numbers will have a least element. So you pick that element, right, and name that as n naught, right? So xn naught will obviously be bigger than L minus epsilon, right? So for the least element, xn naught is bigger than L minus epsilon, right? If xn naught is less than epsilon, then obviously all the elements in the set is bigger than, so all the element for all n bigger than n, for all k is bigger than n, right? So those supremums of those set will be less greater than L minus epsilon. right? So because the supremum of an naught is bigger than L minus epsilon, right? The supremum of an naught is bigger than L minus epsilon. For some n bigger than k, xn is bigger than L minus epsilon, right? So this says, supremum of ak will be bigger than L minus epsilon, right? And that is true for all k bigger than capital N naught, right? So supremum of ak is bigger than L minus epsilon for all n. Right. So now you have two statements. One is here you have for all n, supremum of an is less than epsilon. Here you have supremum of ak is bigger than L minus epsilon for all k bigger than n naught. N is different from capital N naught, right? N is a different value. Capital N naught is a different value. But you have to combine both of them, right? Because if you remember the lim sup is basically the limit of the supremum of AKs, right? So basically you want to show L minus epsilon is less than a lim sup of AK is less than L minus L plus epsilon. That is for some common n. But you have two n's, so the usual procedure is you take the maximum among both the n's. That is what we do. So we will take the maximum. Right, so choose. So I use n naught. So let me choose n1 be the maximum of n comma n naught. Right, so let me choose n1 be the maximum among n and n naught. Then by this line, for all k bigger than n1, so if k bigger than n1, then obviously k will be bigger than n. So for all k bigger than n, k bigger than n, so supremum of ak is less than L plus epsilon from this statement. And if k bigger than n1, then obviously k bigger than n naught. If k bigger than n naught, then supremum of ak is bigger than L minus epsilon. So if you combine both statements, you get L minus epsilon is less than supremum of ak is less than L plus epsilon. Okay. So once you do that, then it is not a big thing, right? So that is what you have. You have for every epsilon positive, there exists n1 belongs to natural number such that, so if you combine this, you can easily see that this is ak minus L is less than epsilon for all k bigger than n. Right? So you have to combine both the statements. You have for all epsilon positive, there exists n1 such that supremum of ak minus L is less than epsilon, right? So from this, you know how to get this absolute value inequality. So this is basically the definition of a limit, right? So this means limit of k goes to infinity, supremum of ak is L. And so meaning of this statement is basically limit of k goes to infinity, supremum of ak is equal to L. So that is the definition of lim sup, right? So you all know right? Hence, right? So this is limit of supremum of AK is denoted by upper limit of xn. So its upper limit of xn is equal to L. Right? So this completes the proof of the theorem. Right? So basically, it is a different characterization of upper limit, right, or lim sup. Right? Similarly, you can have a results for a lim inf as well, right? Lower limit as well. We will put that question in a tutorial problem. Now let us move on to the next theorem, where that's the last theorem for chapter 2. That theorem talks about the relationship between convergence of a sequence and the upper limit and lower limit. So let me write down the theorem first. Let me write down the theorem. Okay, sequence, bounded sequence. First thing, the sequence should be bounded, right? So bounded sequence is convergent if and only if upper limit and the lower limit of the sequence are same, right? So if they are same, the sequence will converge, and if the sequence will converge, then automatically the upper limit and the lower limit are same, right? So we will prove this. Again, two parts to prove. One is if convergence, then you have to show upper limit and lower limit are same. And if it this other way around, if the upper limit and the lower limit are same, then you have to prove that the sequence is convergent. So let's prove one by one. This way, right? Suppose the sequence xn is convergent, right? So if you suppose it is convergent, then you have to show the upper limit and the lower limit are equal. In other words, limit of the supremum and the limit of the infimum must be equal, right? That is what you have to show. Right? Limit of the supremum of this set and limit of the infimum of that set are same. That is what we are trying to show. Okay. Okay, so if the sequence is convergent, then you know there is a limit, right? So let me name that. Right, so since the sequence is converging, it will have a limit. So let me name small l as the limit of the sequence, right? So small as the sequence. So then at the same time, let me say epsilon also positive, because you know for every epsilon we have to do this, or epsilon positive. So because of the limit, there x is n belongs to natural number such that xn minus L is less than epsilon for all n bigger than n. That is a definition of limit we studied at the very beginning of the chapter 2. So we write it down. Now, from this, you have to say the couple of other things, right? So let me recall the definitions we use. Okay, so let me recall. Small mk is basically the infimum of the set xn such that n bigger or equal to k. and capital MK is basically the supremum of Xn such that n bigger or equal to k. Right. So this is how we define the supremum and infimums, right? So denote the infimum and supremum. Infimum small m, supremum capital M. Right. Then, right, as long as the k is bigger than n, right? As long as k is bigger than n, right? If k is bigger than n, then you know this statement is also true, right? This statement also holds for k bigger than n. So xk minus L is less than epsilon, right? For all k bigger than n. So that means L minus epsilon is less than xk less than L plus epsilon as well. So basically you will get this kind of statement. What you have is L minus epsilon is basically less or equal to m n plus 1 less or equal to small mk, that is less or equal to capital Mk, that is less or equal to capital M of n plus 1, that is less or equal to L plus epsilon plus m. That's what we have. Right. Okay, because mn plus 1 is set of all xn bigger than n, right? Capital N. So L minus epsilon is less than xn plus 1, right? So then the infimum is obviously less or equal to xn minus 1, right? And then because infimum is an increasing sequence, right? For any k bigger than n, xn mn plus 1 is smaller than mk, right? But you already know infimum of a set is smaller than supremum of the set. So small mk is smaller than capital Mk, right? And then for k bigger than n, so supremum is a decreasing sequence. So for k bigger than n, mk is less or equal to mn plus 1. But mn plus 1, because of this result, is less than L plus epsilon, right? So basically, we combine a lot of results and write it as a single statement. Okay? So you have this. And so if you combine these two, simply you can say right? So if you take L minus epsilon, M small mk and L plus epsilon, you will get the first statement, right? And then again, if you take L minus epsilon, capital Mk and L plus epsilon, you get the second statement. So from this whole inequality relationship, you have absolute value of small mk minus L is also less than epsilon, and absolute value of capital Mk minus L is also less than epsilon. For all n bigger than n, right? So epsilon is arbitrary. So this is what you have, right? So for every epsilon positive, there exists n belongs to natural number, such that first thing you have small mk minus L is less than epsilon, and capital Mk minus L is also less than epsilon, and this statement is true for all k bigger than n. So from this statement, you can see that from the first inequality, you see that limit of small mk is L, and the second inequality you have limit of capital MK is L, but small limit of small mk is lower limit, and limit of capital MK is upper limit. So eventually you can see that lower limit and the upper limit are equal, and they are actually equal to the limit of the sequence as well. So that is why in the first example you see that both upper limit and the lower limit of the sequence 1 upon n is 0, because you know originally the limit of the sequence 1 upon n is 0. So because the sequence is converging to 0, both upper limit and lower limit are same, and they converge to the same limit as well. Right. Now you have to go to the other way around, right? If the lower limit and the upper limit are same, then you have to show that the sequence is converging and converge to a limit as well. Okay, so let's prove the other way around. Okay, so now conversely, so it was given in the theorem that the upper limit and the lower limit are equal, right? Or lim sup and lim infi equal. So let us name that limit as L, small l, right? Because in the theorem it is only given that this and this are equal, right? For simplicity or for convenience, we name that as L. That is why we say it is L. Okay, so that's L. We say that. So by the theorem we studied, right? By the theorem we studied, right? Because upper limit is equal to L, we see that there exists some n belongs to natural number, n1 belongs to natural number, such that for every n bigger than n, xn is smaller than L plus epsilon. Right? And this part we did not prove, but this is similar, right? So I will give that as an exercise. Okay, so here you have two statements. One is upper limit is equal to small n, right? Upper limit is equal to small l. So by the previous theorem, right? So we prove the theorem we started yesterday and finished today. According to that theorem, there exists a natural number such that xn is less than l plus epsilon for all n bigger than n1. And so this is the theorem we studied, we started yesterday and finished proving it today. You can write a similar theorem like this for lower limit. I told you we will put it in the tutorial, but I write the theorem here so that you can try as a homework. Right? L is the lower limit of xn if and only if for every epsilon there exists n such that L minus this L is same as the other one. L minus epsilon is less than xn for all n bigger than n. At the same time, xn is less than L plus epsilon for infinitely many n. Right? So it's the reverse of the previous theorem, or slightly different from the previous theorem. You try this as a homework, right? The proof is very similar to the previous proof. Only thing is there we are talking about supremum. Here you are talking about infimum. That is the only difference, right? So according to this theorem, you have this results. So now you have two inequalities and two different natural numbers. So first thing you have to combine them. So you obviously know now that always we take the maximum of those two numbers among those two numbers to choose the natural number, which, and so we choose capital N be the maximum among n1 and n2. Okay, so you choose capital N as the maximum among n1 and n2. So then if you combine, then you can combine both the inequalities together for all n bigger than n, because as long as n is bigger than n, it is bigger than n1 and n2. If it is bigger than n2, then L minus epsilon is less than xn. And if it is bigger than n1, xn is less than L plus epsilon. So when you combine all of them, you get this. This is basically the definition of the limit, right? So you all know that, right? So then, so for every epsilon positive, there x is n belongs to natural number such that right. So this means for every epsilon positive, there exists a natural number n such that xn minus L is less than epsilon for all n bigger than n. Right. So that basically it means the limit of the sequence. Right. So hence right. So hence the sequence is convergent, and also the limit of the sequence is basically same as the lower limit and the upper limit as well. So that's what we are supposed to learn in sequences, right? So let me rewind what we did, right? So we at the beginning we talk about what do we mean by a sequence, right? And then we talk about what do we mean by convergent sequence and limit definition like this, right? And then after that we talk about some other properties such as boundedness and monotoneness of the sequence, right? Monotonicity in the sequences. And then we see the relationship between boundedness and convergence, as well as monotonicity and convergence. Especially we talk about bounded convergence theorem and monotone convergence theorem, right? Monotonically increasing and bounded implies convergence, monotonically decreasing and bounded also give convergence, etc., etc., etc. So we studied all those things. And after that we talk about Cauchy criterion for the convergence, right? So we talk about what do we mean by a Cauchy sequence, and then we see the Cauchy sequence is convergent if and only if it is bounded and etc. Right? After that, we talk about subsequences, right? And then we see what do we mean by subsequence and what are the relationship between convergence of a subsequence and the convergence of a sequence. And finally, we talk about limit, upper limit and the lower limit of the sequence, and then the relationship between the convergence of a sequence and the upper limit and the lower limit. And we see example where the upper limit and the lower limit are same, and we see one example where the upper limit and the lower limit are different as well, right? So these are the things we studied in chapter 2, right? That is about sequences. And now we will start the last chapter, right? That chapter is called series, right? So it is basically a slight development from the series. So in sequences you have individual terms, right? So x1, x2, x3, x4, x5, like that, right? So they are basically coming out of natural numbers, right? But they are individual terms, right? 1 upon 1, 1 upon 2, 1 upon 3, 1 upon 4, etc., etc. 1, 2, 3, 4, minus 1 to the power 1, minus 1 to the power 2, minus 1 to the power 3, like that, right? So sequence, you have x1, x2, x3. But in a series, what you're going to do is you're going to have kind of a summation, right? So 1 plus 2 plus 3 plus 4 plus 5 plus, like that. Or 1 plus 1 upon 2 plus 1 upon 3 plus 1 upon 4, like that, right? So that's how you are going to develop series. So chapter 3 is called series. Right. First, right? So you know what do we mean by sequence, right? So we studied in chapter 2. So let un be the sequence of real numbers, right? So from a sequence, what you do is, right? So in basically, so here let me say n is going from 1 to infinity. So this is an infinite sequence, right? Sequence containing infinite elements, u1, u2, u3, u4, all the way up to u infinity. So it keep on growing. So this is a sequence. Then the summation of un, right? So this notation is basically denoted by summation, right? So the infinite series summation of un is the series generated by un. Okay, so series is actually the summation of the terms in the sequences, right? But it will also, you keep on summing, right? So when the first term you have 1, and then for the second term you have 1 plus 2, and 1 plus second, first plus second plus third, first plus second plus third plus fourth, right? So you keep on adding, and things like that. So in that sense, you are basically creating another sequence, right? From one sequence un, you are creating another sequence Sn, which is called as partial sum, right? This sequence Sn is called partial sum. This is going to play a very important role in the series, right? So this is the infinite series, right? So you are taking all possible summations of un, right? So basically, for the first term, you take the first term. Second term of the sequence is the previous term plus second term in the original sequence. Third term is second term plus the third term in the original sequence. Like that, you are continuing, right? So in this way, you are creating a new sequence, and that new sequence is called sequence of partial sum. And this partial sum actually plays an important role in determining the convergence of an infinite series. Right? Because looking at the series and determining the convergence may be difficult. So the easiest way is to look at the partial sum, a sequence of partial sum, and talk about the convergence of the partial sum, because we already know how to determine the convergence of sequences. That is what we studied in chapter 2, right? So instead of talking everything about series separately, if we can reduce the series back into some kind of a sequence, right, then it is easy for us to see the convergence as well, right? So that is what we are going to do here, right? Okay, so the beauty of the partial sum is a sequence, and if the sequence of partial sum converges, right? So you know, not necessarily all the sequences converges, right? Only few of them are converging. So here, if the sequence of partial sum converges, then we see that the series associated with the partial sum is also convergent, right? So if the partial sum is convergent, then the series is also convergent. But in sequences, we say limit, right? So when we say the sequence converges, we say that the sequence is converging to a limit. But when it comes to series, we don't say limit, we will say sum of the series, right? So it's the same, right, as limit, right? Limit of the partial sum is called the sum of the series, right? So let us denote couple of things, right? So finite series, right? So symbol, right? So these are symbols. This you must have seen in A level, right? So it's actually U1, U2, all the way up to un. This is a finite sum, right? So finite series. There are only finite terms in the summation, so that is called finite sum. Right? And then infinite series. So un, let me see. Right? So basically, infinite sum, right? In the series of infinite series, right? It's basically a summation of infinite number of elements, right? K or n running from 1 to infinity. Right? That is basically the limit of the partial sum, right? The limit of the partial sum is actually called the sum of the series. Right? But limit of the partial sum is basically Sn is the summation of first n terms. First n terms is summation of finite series, right? So the summation of 1 up to n uk, right? So sometimes without putting 1 to infinity, we just say summation of un. That means it is again an infinite series, right? So if it is a finite series, we will put up to where the series is going. What are the terms in the series, right? So up to which term are there in the summation. But for infinite series, sometimes we put 1 to infinity, or sometimes we don't put anything. We just put the summation notation and write the term un. Then that means the sequence is a infinite sequence, right? So now these are the basic notations and basic informations about the series. So now, like sequences, we will also see the properties of the series, right? Like sequences, here also we will see different properties of the series, right? Especially, we will start with the convergence, right? So if you want to talk about convergence, then we talk about the convergence of the partial sum. Right? So in tomorrow's class at 1 o'clock, I'll start talking about convergence of series and what are the other properties of the series which are very useful, and also later on we will talk about different kind of tests that will help us to easily identify the convergence of the series, right? So I'll stop here, and tomorrow I will start talking about the convergence of series and other related properties. And so let me stop here and then continue tomorrow.